Okay, so let's just try a little bit more with the standard deviation. Let's make sure we got this. Okay, so you had so these were the ages of 4 students, and we found the standard deviation, or four children, and the standard deviation was 2.5166. Yeah? Okay. 5 years later, how old are these children? 9, 11, and 15. Okay. What's the standard deviation of these children's ages?
We have 5 to
What's that?
just 5 add 5 to.
All right. So what's their standard deviation?
2.5.
Okay. Well, go ahead and try to find the standard deviation of these students if you don't know the answer. I'll let you guys think. Okay, well, you guys started the work, but let's just think about this, okay? So this is 5 years later, and we're talking about the standard deviation of these children's ages. Okay, so who thinks the standard deviation of the children's ages here will be smaller than 2.5166? Who thinks it will be larger than 2.5166? Nobody. Who thinks it'll be the same? Okay, a handful, all right. Okay, and the answer is, it will be the same. Okay, but why? It's not the range, okay? I mean, the range kind of has to do with it. The spread, okay? The spread of these kids' ages, there's still the same amount of spread, right? You know, when the oldest child is 10 years old and the youngest is 4, okay? And then, you know, the middle twins or whatever, okay? They have a certain spread between the ages here, okay? And 5 years later, the gap between the ages between the children, still exactly the same. The same spread. So we have the same standard deviation. Okay. Let's okay, let's say we went to another family, and so we're going to families with lots of children, okay? So let's say they had 5 kids, and these were the spread, and these were the ages of the 5 kids. Let's say we went to another family, you know, so this is like they're taking their kids to soccer practice, and they're like, hey, I think, you know, isn't so-and-so also, you know, the same age? And so you're like, oh yeah, and you also have 5 kids, right? And they're like talking about the ages. They're like, oh, that's so funny, all right? Okay. And then so let's say the other family, the ages are,
Still the same.
okay, which family has more spread?
top one.
Wouldn't they have equal?
I know.
The bottom.
I think it's the same, right?
Okay, so if we talk about the range is the same.
Yeah.
Well, then what about the standard deviation? Which family has the larger standard deviation? So this will be the Jones family, and this will be the Johnson family. Do they have the same standard deviation?
Well, wouldn't it be because
So who thinks the Jones has more standard deviation? Who thinks the Johnsons have more standard deviation? Who thinks they have the same standard deviation? Well, you guys are wrong, all right? The Johnsons have more standard deviation. More standard deviation for the Johnsons, okay? Which has more standard deviation, okay? Again, the standard deviation is how far from the mean. Okay, what is the typical distance from the mean? You can do this by hand, and you'll see that the Johnson does have more. But here, let me draw a dot plot. Okay. So this is 1, 2, 3, 4, 5. Okay, so the Jones family I'm going to put above. We got a dot at 5, 7, 8, 10, and 13. The Johnson family. Here, no, let's go down here. So this is Jones, and this is Johnson. 5, 6, 8, 11, 13. Okay. Can we see a little bit more spread in this one than this one? Can we see that?
Yes.
So even though the endpoints are the same, the 5 and the 13 are the same, we can see that for the middle 3 kids, there is a little bit more spread here than there is up here. Okay? And that will make an appearance in the standard deviation, which takes into account all of the numbers that we have. Yes?
Is that how you said that you could tell by just looking at the numbers?
Yeah, just by looking at the numbers, I can see that this one has more spread. Okay? And we can see, the mean is somewhere, around 9-ish, 8 point something. Yeah.
Can you also tell by for the Johnson family, the fourth number is higher than Jones, like it goes up?
Not necessarily. Okay. So if we found the mean for both families is 8.6. Okay. So 8.6. This is where the mean is, and we can ask, how far is each point from the mean? And we see that this point and these points are the same distance from the mean, and these guys are the same distance, and these guys are also the same distance. But this one is only this far from the mean, whereas this point is this far from the mean. And this guy is this far from the mean, and this guy is this far from the mean. So we can see that these children, when we look at this children versus the distance from the mean is bigger for this one and this one than it is for this one and this one. Okay? Again, standard deviation is a measure of spread. And when we put the make a dot plot and we look at the individual points, I hope we can see that there is a little bit more spread for these dots than these ones. Is that okay?
Yes.
Okay, and so this one will have a larger standard deviation. All right. The standard deviations are incredibly useful to us, okay? There's a reason why there's so much emphasis on this quantity, the standard deviation, okay? Because the standard deviation can be used as like a measuring stick. And what I mean by this okay, let's say we're talking about some mysterious animal. Right? Let's say you've grown up very sheltered, and you've never been to the zoo, okay? But then you meet a friend, and he works at the zoo, and he's very excited about the zoo animals, okay? And so let's say you've never seen, let's just make up an animal, okay?
Elephant.
What was the, okay, what was that? What were those animals in Harry Potter? No, the Thestrals. Okay? You can only see them if you've seen them. All right. So you've never seen a Thestral before. Okay? You guys know what I'm talking about? All right.
Yeah.
It doesn't matter. There's some animal called the Thestral. All right. And then so you're talking to Hagrid, and Hagrid's like, "Oh, I'm so excited. These Thestrals, they're so beautiful." Okay. And you say, and so Hagrid tells you, I saw the most beautiful Thestral the other day, and it had a wingspan of 12 feet. And you're like, okay, that sounds nice. And he said, no, you don't understand. The average wingspan of a Thestral is like 11 and a half feet, and this wingspan was 12 feet. And you'd be like, that doesn't seem like a big deal. It's only 6 inches larger than average, right? So, but Hagrid's obviously very excited for this wingspan of 12 feet, where the average is only 11 and a half feet. Okay? And he says, no, you don't understand. Okay? I've seen hundreds of Thestrals, and almost every single one has a wingspan, maybe 11 and a half feet. If we're lucky, they'll be 11.6 feet. Maybe most of them are 11 and a half, 11.5, 11.52, 11.45, 11.6 unusually, and this one was 12, okay? And so only after Hagrid goes into this thing and lists off all of the other wingspans and gives you an idea that Thestral wingspans follow this very tight range, right? How do we say that?
Small spread.
It has a small spread. The wingspan of Thestrals generally follows a very small spread. So almost every single Thestral born has a wingspan of 11 and a half feet, okay? Give or take just a few, tiny bits. And here was one Thestral where the wingspan was 12 feet, okay? And then after understanding that the Thestrals have such a small spread, then you can appreciate how this one Thestral had a 12-foot wingspan. Does that make sense? Okay. So what Hagrid can also do is he can give us something called a z-score, all right, which uses the standard deviation. So rather than saying, okay, so to get this idea, we had to first understand, what is the average wingspan of a Thestral, and then we had to understand that the spread of wingspans is also very, very small. That almost all the Thestrals have the same type of wingspan, and only very, very rarely do we see a wingspan much larger than that. Okay. The standard deviation gives us an idea. If we're told that the standard deviation of Thestral wingspans is like 0.1 feet, okay, then we can appreciate a difference that's much larger. So so here's our little example. Very excited about the Kestrel with a wingspan of 12.0 feet. Okay. The average or the mean wingspan of a Kestrel the spread of wingspans, the spread of wingspan lengths is very small. Okay, so most wingspans are from, let's say, 11.4 to 11.6. Okay. Rarely is it above that. So a wingspan of 12.0 is rather remarkable. Okay. So we can, by knowing the standard deviation, okay, so rather than having Hagrid have to list off all of these different wingspans, he can just tell us, oh, you know, maybe you need to know that the wingspan has a standard deviation of, let's say, 0.1 feet. Hagrid can also tell us Hagrid's our friend. He lives in a hut. He's the gamekeeper. School grounds. I guess I could have talked about unicorns. Unicorn horn lengths. I don't know, whatever, okay? You wouldn't believe it. This unicorn had a horn that was 3.5 feet long. It's beautiful. Okay, so does this make sense? So at first when you hear, oh, average wingspan is 11.5, and this wingspan was 12, that's only half a foot more. At first it doesn't seem very impressive. But once you learn that the standard deviation is very small, then you can appreciate how different this one is, right? I hope that makes sense. So I'm going to introduce the concept of a z-score. A z-score, or if you are British, a z-score, okay? A z-score tells us the number of standard deviations a point is from the mean. Okay. So this Kestrel with a wingspan of 12 feet is how many feet larger than the mean?
Half a foot.
Half a foot. So 0.5 feet has a wingspan that's 0.5 feet larger than mean. And if each standard deviation is 0.1 feet, how many standard deviations away from the mean is this vector? 5 standard deviations. 5 standard deviations. So this vector would have a z-score of 5. Okay. Let's try a few examples here. Okay. So if we're talking about men in the United States, the average height, the mean height of a man in the USA is, does anyone know? 5'10", 5'9", we'll say 69.5 inches. Okay. So whoever wanted 69 before, here you go. Okay. And let's say the standard deviation is 3 inches. Okay? So how tall is someone who is 1 standard deviation above the mean?
72.
So a man
30.5.
who is 1 standard deviation above the mean is 72.5 inches tall. Does that make sense? And what would this person's z-score be?
1.
Positive 1. The z-score is +1. Does that make sense? No. It doesn't? The z-score is the number of standard deviations a point is from the mean. Okay? The mean is 69.5. Does that make sense? Yeah. Okay? The standard deviation is 3 inches. So if I'm 1 standard deviation above the mean, how many inches above the mean am I? I'm 3 inches above the mean, which puts me at 72.5 inches. I just added 3. Are we struggling with the decimal? Should I get rid of the decimal?
So the z is pretty much saying we're 1.
Yes.
Set of
Yes.
3
Okay. Well, hang on. So are we okay with this part?
Yes.
A person who is 1 standard deviation above the mean is 72.5 inches tall. Anybody having trouble with that?
I
Yes.
have a question about how do you get the, do you give the standard deviation?
Yeah, I'm just giving you. Okay, this is given to you. Okay, I made these numbers up. Okay, I didn't make them up. They're based on facts. Okay, but I'm giving you these numbers. So I said, how tall is someone who's 1 standard deviation above the mean? 1 standard deviation is 3 inches. This person is 3 inches above the mean. So 69.5 plus 3 inches, 72.5. Okay? Is that good? All right, how tall is someone who is 2 standard deviations above the mean?
75.5.
I do 69.5 plus 2 times 3, which is 6 inches, gives me 75.5. Okay? So 2 standard deviations above the mean, 75.5 inches. Okay? And this would have a z-score of +2. Okay, because the z-score just tells me how many standard deviations above the mean or below the mean am I. Okay? Yes?
Could you say somebody is under the...
Yes, absolutely, absolutely. Okay? So how tall is someone? If I said their z-score is -2, how many standard deviations from the mean are they? Not how many standard deviations. If their z-score is -2, they are 2 standard deviations below the mean. So how tall is that person? 63.5. So if the z-score is equal to -2, the person is 2 standard deviations below the mean. Okay? The mean is 69.5. Each standard deviation is 3 inches. So 2 standard deviations below is 6 inches below. 63.5 inches. Is that okay?
Yeah.
All right. What is the z-score? Or, okay, anybody having trouble with this before I keep going? All right, what is the z-score of a man who is 5 foot, so not, we'll say 67 inches tall? Okay, again, the mean is 69.5. And the standard deviation is equal to 3. What is this person's z-score? Do we have an answer? Yeah?
Is it negative 2.5?
No, not the z-score. Okay.
I don't know.
You guys are getting stuck.
0.83.
Don't get, huh?
0.83.
0.83, but negative. Negative 0.83. Okay, my answer is z is equal to negative 0.83. I'll explain.
0.83 below.
How tall is this man? 67 inches. What is my mean? 69.5. So how far away is this man from the mean? 2.5 below the mean, right? So I could do 67 minus 69.5, and I see that this person is 2.5 inches below the mean. Okay? How big is a standard deviation? 3 inches. So how many standard deviations is this person away from the mean?
1.83.
Yes, I'm going to take this and I'm going to divide by 3. So when I divide this by 3, I say this guy is 0.833 standard deviations below the mean, right? If he was 1 whole standard deviation below the mean, how tall would he be? He'd be 3 inches shorter than the mean. But he's not 3 inches shorter than the mean. He's only 2.5 inches shorter than the mean. So he's not quite 1 full standard deviation below the mean. He's only 0.833 standard deviations below the mean. Does that make sense? Yes.
Is there any formula that we can use?
Yeah, there is a formula, okay? But I wanted to get you guys to understand this concept first. Does this make sense?
Yeah.
Okay. How tall is someone whose z-score someone whose z-score is 1.33.
No.
73.49.
Yep, 73.49, 73.5, okay? So, again, as z-score tells us what? How many standard deviations we are from the mean. How many standard deviations away from the mean is this person? 1.33 standard deviations above the mean. How big is a standard deviation? 3 inches. So how many inches away from the mean is this? 3.99. Okay, so each standard deviation, so this person is 1.33 standard deviations above the mean. Okay, each standard deviation is 3 inches. So 1.33 times 3 gives me 3.99 inches. Okay, or 4 inches And if the so this person is 3.99 inches above the mean. Which is 69.5. So I do 69.5 plus 3.99, which is 73.49, or basically 73.5, okay? Do you understand or don't understand?
So when it's more, we just multiply it to the SE, standard deviation?
Yes.
And then carry on.
Okay, so again, what does the z-score tell us?
How many standards?
How many standard deviations we are from the mean. Okay, so this is how we find a z-score. A z-score is we take the point, and what do we subtract from the point? The mean, okay? And this gives us what? If I do x minus x bar, this tells us what?
How far away it is from the mean?
How far we are from the mean, okay? This is subtraction, right? What does subtraction tell you? It tells you how far apart are two numbers, okay? Sometimes when we learn subtraction, we don't realize actually what subtraction is, okay? But I don't want to know how far away that is. I want to know how many standard deviations it is. So I divide by s. And this is how I find.
Could you write that in? Like, not by formula?
Well, okay. I mean, I did up here also. Basically, we're taking the distance and then we're turning it into standard deviations. So I can't make that any simpler than what it is. I'm sorry. Yes.
So the x is like whatever information that
Yeah. What our point is, and I'm finding the distance from the mean, but I don't want to know just the distance in straight values. Okay. Like Hagrid can tell me the wingspan is half a foot longer than the mean. Is that good or bad? I don't know, okay? But I want to know how many standard deviations. A person is 6 inches taller than average. Is that amazing or not? We don't know, okay? When we find out that the standard deviation is 3 inches, then we're like, oh, okay, this person is 2 standard deviations above average, okay? So this is a z-score, okay? And do you understand how this formula for finding the z-score, x minus the mean divided by the standard deviation, relates to the definition of a z-score, okay? Because it tells us how far we are, the distance from the mean, but then we divide by the standard deviation to see how many standard deviations we are from the mean, okay? Yes?
But in this one with plus 1.33, we're subtracting, so if it was in that case,
we are, okay? So let me just show you how the z-score formula can be used for these things, okay? So here we know x bar is equal to 69.5 and s is equal to 3, okay? So here I said, what is the z? What is z of 67? 67. So I said z is equal, this is my x, I do 67 minus 69.5 divided by standard deviation 3. I get negative 2.5 over 3, negative 0.8333. That's what I did. Over here, I said, what is the height, or how tall is someone whose z-score is 1.33? So here I'm asking for what is x? Okay, z is equal to 1.33, and x bar, again, is 69.5, and s is equal to 3. So now I have, using z is equal to x minus x bar over s, I have 1.33 is equal to x, which I don't know, minus the mean, 69.5, divided by s, which is 3. And so I multiply both sides by 3, and I get 3.99 is equal to x minus 69.5. And I add 69.5 to both sides, and I get 73.49 equal to x. Which is what we've done, both sides. How's that? Good? I hope. Alright, so what does standard deviation tell us?
How far away each point is from the mean?
Spread.
Standard deviation is a measure of spread, okay? And it gives us a typical distance from the mean, okay? What does the z-score tell us? The number of standard deviations we are from the mean. Okay, so let's just see if you understand this, okay? All right, so I'm going to ask some questions. See if you can come up with a thought in your brain. Don't blurt it out, and then I will give you the answer, okay? So I'm going to tell you, women, okay, let's say for a certain demographic, let's say the average height of a woman is 64 inches tall, and the standard deviation is 2.5 inches. 2.5 inches. Okay. So in your brain, see if you can tell me how tall is a woman whose z-score is 1. The mean is 64. Don't blur it out. The mean is, all right, so I'll put this on the board. Okay? The mean height is going to be 64 inches. Standard deviation, 2.5 inches. How tall is a woman whose z-score is positive 1? Don't blurt it out, okay? Just think of it in your head. Or write it down on your paper. Okay. If the z-score is 1, she is 66.5 inches. Okay. How tall is a woman whose z-score is negative 2? Think of it. Z-score is negative 2. How tall is she? Don't blurt it out. Think. So negative 2, she would be 59 inches tall. She's 2 standard deviations below the mean. Each standard deviation 2.5. So she's 5 inches shorter than the mean, 59 inches tall. Okay. Who didn't get that one? Okay. What's 63.5? So her z-score is negative 2. So how did you get 63.5?
I don't think I did it right.
Okay, I'm sorry. Okay. So just be careful. Okay, what is a z-score of a woman, this might be 2, who is 69 inches tall? What is her z-score? Just think in your head. So if she's 69 inches tall, her z-score is positive 2. Positive 2. She's 2 standard deviations above the mean. Okay? Now other problems might require a calculator, okay? So, yeah, go ahead and pull out your calculator and see if you can tell me. What is the z-score of a woman who is 68 inches tall? What is the z-score of a woman who is 68 inches tall?
You could do this. You're trying to.
So just get it in your head. Okay. Are you guys even trying? You got it? Okay. And the answer is 1.6. Okay. She's 68 inches tall. She's 4 inches above the mean. But we don't want in inches. We want in standard deviations. So 4 divided by 2.5 is 1.6 standard deviations above the mean. Alright? Is probably okay? Okay, so I know some of us got it. And then others of us that maybe don't or too shy to say anything. Okay. When we look at z-scores, when we compare z-scores, we can get an idea of what is more extreme. Okay? So this is known as the empirical rule. Okay? And this is for if we're looking at a numeric variable that's unimodal and symmetric. Okay? 68% of the data, so a little bit more than 2/3. About 2/3 of the data is within one standard deviation of the mean. Okay? So that means they have z-scores between what and what? What does it mean to be within one standard deviation of the mean?
Between like 66.5 and
1.5.
61.5.
Exactly, exactly. Great. So this means we are no more than one standard deviation below the mean and no more than one standard deviation above the mean. Okay? So z-scores are between -1 and +1. Okay? So this tells us that about 2/3 of women are between basically 61.5 inches tall, so 5'4" minus 2.5 inches, to 64 plus 2.5 inches, so 66.5 inches tall. Okay, so this is 64 minus 2.5 gives me 61.5, and this is 64 plus 2.5 inches. Okay? So 2/3. 2/3 are within one standard deviation of the mean. Okay? And 95% of the data is within two standard deviations of the mean. Okay, so that means z-scores are between what?
69.
No, z-scores. Z-scores are between -2 and 2. Because how many standard deviations? No more than 2 below and no more than 2 above. So -2 and 2. And within 3 standard deviations of the mean, 99.7%. So almost everybody. This is almost 100%. Okay? But not quite. 99.7% is within 3 standard deviations of the mean. So if I go 3 standard deviations above or below, I get almost everybody. Almost everybody. And that's the empirical rule. And by comparing z-scores of measurements, we can decide if something is more extreme or not. Okay?
Quick question.
Yes.
This 68% to 95% to 99.7.
Yes.
That is all part of the empirical rule.
Yes.
All right.
z-scores. We can see if something extreme than the other. Okay. All right. So I'm just making up numbers. What's the average weight of a dog? What do you say?
25 pounds.
15 pounds.
So it depends, right? We're getting all kinds of answers, right? But let's say, because we got little dogs and we got big dogs and things like that. So let's just say I'm making up a number. Let's say the mean weight of a dog is 55 pounds. Okay? And let's say the standard deviation is 20 pounds. Okay? And what would you say is a big dog?
100 pounds.
A dog that's 100 pounds, you'd say is a big dog, right? Big dog. Big dog, 100 pounds. Okay. What would you say is a big cat? House cat. Okay, so let's say I got a friend and her house cat is 23 pounds. Okay, you'd say that's Tubbs McGee. All right. We got all right, and maybe the mean weight of a cat. I don't know. What's the average weight of a cat? 12 pounds? 13 pounds? Who knows? I'm making up numbers. Standard deviation, let's say, is 3 pounds. Okay, tell me, what is the z-score of the dog and what is the z-score of this big cat? Go, 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 go. This is what we got. 2.25 and 3.333. You guys need another moment? Alright. I'm just feel like I gotta speed things up because I want to talk a tiny bit about your lab. Okay, so here I just did 23 minus 13 divided by 3, 10 over 3, 3.333. And over there, 100 minus 55 over 20, 2.25. So here I've got a z-score of 3.33 and a z-score of 2.25. Both of these are pretty impressive, okay? Generally, z-scores of more than 2 or more negative than minus 2 is considered unusual, okay? Because what did we say? How much is within 2 standard deviations of the mean? About 95% is within 2 standard deviations of the mean. So this means that, only about 5% has z-scores larger than 2 or more negative than negative 2. But here we've got the bigger z-score, so this z-score is farther away. So the z-score is more extreme. So the 23-pound cat is more extreme than the 100-pound dog.
Did we make up the SD?
Yeah, I made up the SD for both of these. I made up the mean and standard deviation for all of these things. But I mean, if you're given a mean and standard deviation, you got to be able to find z-scores for things like that. Okay?
Is that negative 10/3?
No? That's just residue from previous. Yes?
So my question is when you're gonna ask for z-scores, you're gonna provide a mean and a standard deviation.
Yeah, I'll give you a mean and standard deviation.
And the pounds of the dog and the cat, is that something that is like, for example, that we have to find
Yeah,
out?
I mean, so if I give you this problem, you've got to be able to give me a z-score. Okay? Yeah.
I don't quite understand how you implied the empirical rule to decide it.
I didn't imply the empirical rule.
Or how, like, did you decide that the cat's more extreme?
So here's 3.33 versus 2.25. Which number is farther away from 0? Which one's bigger? 3.33 is bigger than 2.25. This one's more extreme. Okay? If we were talking about negative numbers, then negative 3.33 is more negative than negative 2.25. Okay, hang on. I want to talk about the lab that you guys have. Okay? Alright, so this week when you check your homework, okay, it says you got to do all of these problems, okay, and I just talked a little bit more about z-scores and some stuff. And here's some videos that I think are helpful, okay, and I recommend watching those. And so this is one assignment, and then you also have the lab, okay? And the lab says use StatCrunch to complete exercises 2.24, 3.5, 3.11, and 3.39. Okay, so basically you're going to do problems from the book, but you're going to use StatCrunch to answer it. Okay. Now, if you have Microsoft Excel, you might be able to do some of these problems using that. Okay, but I'm not going to provide guidance for you to do that. Okay, so I've provided some guidance in the forms of videos and stuff to do the problems on StatCrunch. But if you're comfortable using Excel to answer some of these questions, you can do that. I'm not going to force you, but what you got to do is you're going to go to StatCrunch. So here, let me see if this works. So you go to StatCrunch, and then you're going to have to sign up if you're going to use StatCrunch, and you sign in, okay? And what you're going to do is you're going to choose Open StatCrunch, and then sometimes this will pop up, okay? You got to have Java installed on your computer, and this is a lot of people have problems getting Java installed on their computer or things like that, okay? You might be able to ask a friend to help you get Java installed. For some reason, Google Chrome doesn't play well with StatCrunch. Sometimes it works, sometimes it doesn't. If you're using a Mac, Safari generally works. You just, you got to pay attention to the edges of your browser, because sometimes little pop-ups will show up, or little buttons that will say enable or disable. So just make sure you always enable the things. If you, on PC, Internet Explorer and Firefox work well. Chrome, for whatever reason, has problems with StatCrunch. I don't know why. Okay, so anyway, you can update or whatever. I'm just going to say later, and it will load Java, and this is what should appear here. Okay, and it looks like a spreadsheet, and you can use these things. Okay, so a nice thing about StatCrunch is it can load data, and I can say load from a web address or from a computer. So from here, I can just copy these links. So I can say copy the link shortcut and load it from a web address. I would say use tab as the delimiter. I think in the help video I said white space is fine, but generally tab will work better. And when you do that, the numbers get entered into the computer. Okay. If you're using Excel, you might be able to open it as a tab delimited file or something like that. But I won't provide guidance. Yes.
So the problems you listed on your page are the ones we have to do?
Yeah, so it says do these problems from the book using StatCrunch, okay? And so basically from here you're going to try to make some dot plots or something. So you can do graphics, a dot plot, we're going to create a graph using baseball. And so this is, so you can kind of see it, but there's a dot plot that it made using our baseball weights. Okay, we can also create histograms. Make a histogram. Oops. And sometimes if you there's different options, but I will. We got messed up, but basically we would probably have to prefer to have the same bin width. But we can see a histogram for the soccer weights and the baseball weights, and we can answer questions about it. So anyway, this is StatCrunch. You need Java on your computer. So if you're having problems, just check if you've got Java installed and see if you can get a friend to help you get Java installed on your computer. That will probably be 95% of your problems. And once you get Java working, the StatCrunch should work just fine. Yes?
And we'll be turning in our work from what problems you do.
Yeah, so you're going to, what I would like you to do is, once you produce a graph, you can do option copy, okay, and then you would open up something like Word, or whatever, and then you can just paste the graph right there, and then you can say, and answer the question. In this histogram, because the book asks you to make the histogram or something, and then asks you questions about them. So be sure you answer the questions from the textbook problems.
And you wish this to be printed, or?
Yes, please print it. Okay, it does not have to be color. You don't have to print a whole bunch of pages. Just print them and then and turn it in the same pile as you do your homework. Okay. There is a quiz next week.